variables. But of course, here we should be careful about the notation. Yeah, so we have the notation of x to the power a. So we should remember what it means, right? So take the components of the vector a and then raise the corresponding variable to the correct powers, right? So we have, so in the old notation, this x will be the first variable and so on, right? So okay, so let's try to compute the degree complex delta 0 of I and delta a of I, where a is either of the following vectors. So 2, 0, minus 2, 0, and 1, 0, 0, 0. Yeah. And by this vector 0, I mean the vector with all the components means 0. So we try to compute these simply so complexes. Yeah. So firstly, we recall the definition, right? So by definition, for this first we have to compute the negative.
Professor Hope, how did you choose this vector A?
I mean, if you want, you can choose also another. There's some reason, but I don't want to be too specific at this point. So can you choose another vector for me, maybe?
There is no specific reason to choose.
Yeah, no.
Okay.
Yes.
Okay.
Can you pick another vector? I will be happy to do with that. And I will start with that vector anyway. So take another 4-component vector, please.
This A should be a vector which is not coming from the generator of I.
Yes, it is a good remark. Yes, yes, that's one of the reasons why I take this. But I mean, we can start with just any vector you want.
And we can take the negative entries too. You take -2 too. So this, can you elaborate more about this vector? So this vector is coming from all integers, Zn, Z4?
Yes, so there's no, I mean, here's the only requirement is A belong to Z to the 4, yeah? And that's it. Yes. So we have 4 variables here, so the A should be in Z to the 4. As you see here, if you have D variables and your vector should be Z in Z to the D, and that's all. Yeah.
Actually, most of the people just arrived. Can you just repeat, arrive now? So can you just repeat from the beginning what you are going to explain? Yeah, okay. From the beginning, yeah.
So in the end, we want to work with the problem about maybe I take another slide here. So in the end, we want to look at this problem. We want to study whether this limit exists. Where I is just any homogeneous idea in a polynomial ring. Yeah? Okay, and then it is easier to start with a case of monomial ideas. And as I told you in the case, and sometimes even unmixed monomial ideas. Actually, this is the most interesting case. The unmixed case is more interesting. And I told you that in the unmixed monomial case, we have a way to compute the symbolic powers of a monomial idea, right? So I told you that you can start with a redundant primary decomposition. And then from this, you can compute, at least in theory, all the symbolic powers. Hence, the intersection of powers T power of Q1 up to Qs. Yeah. And then what I'm telling you right now is to look at the Takayama formula. And this is useful because this Takayama formula tells you the local homology of just any monomial idea, yeah. Any Poisson ring R mod R, where R is a monomial idea. So including these symbolic powers, yeah. So if I is a monomial idea, then all the symbolic powers of I are also these I didn't tell you, but these are also monomial ideas. And if you start with unmixed, then these are also unmixed monomial ideas. Yes, and then so the good thing about Takayama is that it gives you the formula for the local cohomology. It computes in terms of some reduced simpliso homology. Yeah. So in the end, what I was trying to write in the last in the end of the last lecture is this formula. Yeah. So and this we know that the depth can be computed from this. The depth is computed as the minimal I, such as the I local cohomology of this is non-zero. And this is something that we can roughly speaking, this is some combinatorial object. That so this is if you have a simply so complex like delta I, then you can write down the.
So A is a positive integer here, right?
A can be any vector with D components. Yeah, D is the dimension of R. Yeah, any integer vector, not necessarily positive. Yes, so that is the plan. Yeah, and now we are at this complex. We want to see this complex in action. Yeah, this simply so complex in action. What it is. Okay. So coming back to our example. So here, if you want,
so in the Takayama's theorem, so we can compute that cohomology for any possible value of A coming from
yes.
Zn, right?
Yes, yes.
And how it relates with the depth then? We For the depth, we have to compute the minimum value of I for which the cohomology is not equal to 0 and independent of A.
Yes. So yes, the formula would for that would be like this. So yeah, it is.
So it really doesn't matter that how one choose A, right?
So of course, it will depends also on A as well. So you have to take like the minimum of uh, combining these two formulas, then you get that the depth is the minimum of J plus the cardinality of the negative support of A, such that this reduce simply so homology is non-zero plus one, sorry. So here I take J to be some integer. J can be negative and A is some vector in Z to ZD. Yeah? So this will be the formula for that in terms of the degree complex.
So it really doesn't depend for which value of A we are doing. So A can be any vector, right? Or any
No,
collection
no,
of vector.
no. Here, I mean, it depends on
Yeah.
A. Yes, so you have to work with many A's. Yes, so in this formula, but yeah, at some point, you can restrict to some special class of A. So at some point, for example, you can you only have to work with A in a small set. Yes, we will come to that point. So you can also take, for example, A to be minus 2, minus 2, minus 2, minus 2, for example. Yeah, doesn't matter. To do example, you can choose anything. Yeah. So I compute this first because it is actually the first important complex. So delta 0 I. So recall that for delta A of I. Yeah. So for delta A of I, first we have to compute the negative support, and then we take all the difference where F is something containing the negative support of A and contained in the set of integer from 1 to D, such that x to the A is not contained in I localized at F. Yeah. So in this case, we see that the negative support of this is, of course, the empty set, right? The zero vector has no negative component. Okay, x to the A, x to the 0 is 1, right? And okay, so from this formula, you see that delta 0 of I is all the F is in 4, right? So in this case, we can write this set as x, y, z, t. Yeah. So we regard the index directly as a variable. And now our condition is that one is not in I localized at F, right? And you see one. So if you ask when is one belong to I localized at F, then this would mean one recall that this is R and you localize everything in F. Yeah. you invert everything in F. So this is just the localization of R as the products of the variable in F. And that's it. Yeah. And so one belong to this means that so if you clear the denominator, then this means that products of the variable in F, right, raised to some power would be in I, right? So for some non-negative integer t.
By
And so
RF, you mean the R localized with F with respect to F? By
yes.
RF.
Yes, yes. This is the meaning. Yeah. The same as inverting all the elements in F, all the variables in F more precisely. If we regard as a subset of the variables, then this means inverting all the variables in F.
And how you are constructing GA?
Yes, ZA is the negative support. So all the I in D such that the I component of A is negative. Yeah. So if A is outdoor zero vector, then this is an empty set, right? All the components of this are zero, so no negative components. And so you see that one
So
is
G1 is going to be something with -100. For instance, if I have
remember that this is a vector. Yeah, A is a vector in CD.
yeah, it's a vector. Yeah. Okay.
Okay, so
I understand.
So you see, one belong to I of RF is equivalent to products of things in F. Yeah, belong to the radical of I. Right? So that's it. So in our case, I is EQ YZT, and so the radical of I is just X and YZT, this square trinomial idea. And so you see that products of variable in a subset belong to I. Yeah, so or I do the other way. One does not belong to I localized at F. If and only if. So this means that a product of elements in F cannot be divisible by X or YZT, right? So you see that the only choice for F is one of these. Yeah? It cannot contain X, so only smallest one is empty set, and then you can take a subset of YZT, but not YZT itself, right? Because it also cannot be divisible by the product YZT. So these are all the things that you can get. Okay, so yes, so in the end, that was our first computation. Yeah. So delta zero of I. This actually is what people call the Stanley-Reisner or the simply so complex corresponding to this. Yeah. So this will be the Stanley-Reisner idea of this complex, and this complex is exactly this guy that I was writing. So I will copy it again. This simply so complex. Okay, and one thing that we can prove this we can prove later, but actually it is also not difficult. It is so we always have this is somehow the biggest complex among the degree complex. Yeah. It F minus the negative support belong to delta AI. Then F actually belong to delta zero I. And this is true for every monomial ID I and for every monomial ID I and for every vector A in Z to the D. Yeah. It is delta zero. Okay, so next we compute the other delta AI. Yeah? So our next A is this one, 2, 0 minus 2, 0. So again, we compute the negative support first. You see that it is in the third position, so it is Z. Yeah. X to the A in this case is x squared Z to the minus 2, right? So by our definition, delta, the degree complex of I with respect to A is all the difference F minus GA with x Z, yeah? And Z should be contained in F and contained in x, y, z, t. And such that x to the A, which is x squared Z to the minus 2, is not belong to I localized at F. Yeah? So it is easier to use this lemma at this point. Yeah? So we know that F, if this is an element in this complex, then at least F belong to delta zero, which we have computed. Yeah? It is now delta zero. So already you see that F must contain Z. So F can only be Z and Z, Y, Z, T. And that's all Z, Z, Y, Z, T, everything that can contain Z in delta zero. And then you just check, yeah, you just check. So for example, F equal to Z is it okay? So you check whether x squared Z to the minus 2 does not belong to I in invert localized at Z, and you see that Z is okay, right? Z is equivalent to x squared Z to the T minus 2 does not belong to I or OT at least 1. And recall that I is generated by x to the cube YZT, right? So something like this can never be divisible by x to the cube or YZT, right? Here you have only power 2 x squared, so this cannot be in I. So this is okay. So this is allowed. And similarly, you can check that this is also allowed, right? X squared Z to the cube does not belong to I. I localized at Y times Z, right? So equivalent to x squared Z to the minus 2 YZ to the T does not belong to I for all t at least one. And z is also true. Yeah? If z is belong to I, then this must be divisible by either this or this. But okay, this sorry, here I should not use t because it is confusing. Maybe I use c also here because t was some variables. But in the end, you see that this cannot be divisible by x cube or yzt. So this is okay. So z is okay. Z is okay, and z is also okay. So in the end, what is delta?
Excuse me.
Yeah.
It is better to just mention that what kind of localization you are using for the participant. So this is
yes,
okay.
of course. So for f is this, then you localize as a product of y and z. Yeah. But at this point, then you are clearing the denominator, so there's no localization here. This is true for all c. This one.
So just define RZ particularly so that they can understand why this is not equal. This is not containing in IR by Z of other inequality.
Yeah. I mean, this is just so. Yes. So maybe here is just to recall you that this localization. Yeah. Is you can just take localization at any element of any element W in R. Yeah. Then this is the set of all elements of this type have to the sum power W. Yeah. That is the so the localization of R at W.
Thank you. Thank you.
Mm-hmm. So you see, this is in the end F substruct to Z, where F is either Z or ZT or ZY, right? And so that is to say, this is this complex with tree set, yeah. So 0 empty set Y and T. Okay, so what else do we have? So I think at this point you understand what is going on. So I just write out quickly the result. Yeah. So in the case this, I want to compute this.
Herb.
Yes.
Sorry. So then I think in the case where f equal to yz, then I think the localization at r at f. So then now I think the localization should be the multiplicative set that is generated by z and y, right? This is not just y times z, right?
But it is actually the same. Yeah? You are right, but
so here I think then you have more power. So then y and z can have a different power. They
They
I
can't
know,
have different power in the denominator. I think YZ can grow together.
But you can clear the denominator, right? So you can have something like f to the y to the n and z to the n, and you can clear the denominator, right? F to the times something to yz to the maximum of y.
Okay.
And,
Yeah.
right?
Yes. Okay.
Okay.
Mhm. Yes. Okay. So I mean, in this case, b equal to this, then VB is the empty set, right? The negative support is empty. And okay, and if you compute, then so you see that's the what is the condition for some f minus VB, which is f itself, right? F belongs to delta B if and only if x to the b. What is x to the b? It is x, right? And this should not belong to I localized at f, right? And you can check that, okay, again, f, as we said above, f should belong to delta 0, right? And in this case, everything in delta 0 is allowed. Yeah? Recall that in delta 0 we have this, yz, yt, and zt, right? And you can check that everything in this is allowed. Yeah? So for example, even this one is allowed because this is not belong to I localized at z times t. Yeah? Recall that our I is xq yzt. Yeah? Yes, so in the end, our delta b I is exactly delta 0. So my last example in the list is this one. So all the negative component. Yeah? So C equal to okay, again A minus 2 minus 2 minus 2 minus 2. So in this case, the negative support of A is everything, right? X, Y, Z, T. So if you want to have something like this in this complex, then as we said above, yeah, this F must belong to delta 0. And on the other hand, it must contain the negative support. And you see that this is not possible, right? So there's no F like this. And so this tells you that this is an empty complex, no face at all for this case. So yes, so that is some of our example. So maybe we can compare. We can try to use Takayama.
Excuse me.
Yes.
My message to IBA Karachi participant. If you have any question, you can interrupt. So anytime you can ask the question. So there is no need to place your questions on the chat box. So you can ask directly if you have any questions. Sorry, Hope.
Okay.
So we have, we have some participants sitting in Karachi, and there are a group of participants who are in Lahore.
Yeah, you can raise it.
Please go ahead. Go ahead. What is your question?
आपको मेरी आवाज क्लियर आ रही है?
बिल्कुल आ रही है. So you can. Okay, go ahead.
My question is that you are taking the component minus 2 in x, y, z, and t. So why you choose minus 2 only?
Again, that was chosen randomly. I'm sorry. Yes, there's no particular reason. Yeah?
So if we take 2, not the sign negative, take the positive value of positive integer, what's happened?
Sorry, what is your example?
So, Hope, do you understand the question? If yeah.
What is your A now?
I'm saying that you are taking minus 2 and minus 2 for component x, y, z, and t. If you take plus 2, what's happened in all the equations and variations?
You want this example, right?
Yes.
Okay. I was just trying to show you that the computation depends on how the computation depends on A. Yeah, and that was all what I was trying to do. Yeah. You can take, you can also take this, yes, and yeah. I think what you get is also delta zero. It seems to me that if you take this, then this no yeah, we have to this we have to this we have to compute, yes. So I leave it as an exercise to you, yeah, to compute this. Yes, it is interesting, but it is also not that difficult. So maybe what we can do now is the following. So we try to compute the following. This and this. Where again I is as above, yeah. I and R as above. And A is one of the two first derived. Yeah. So actually we know something beforehand, before even using Takayama. Yeah, we know that the depth of R mod I. In this case, you see that I is generated by a regular sequence of length 2, and R has dimension 4, so this should have depth 2. Yeah. So we know beforehand that this should be 0. Yeah. Because that is the minimum value such that you have non-zero local homology. So let's try to check whether it is true by Takayama. Right? So I will do only this case, and this I leave as an exercise. Yeah. And I compute dimension of the greater piece of the first and the second local homology at this degree I, yeah, at this degree.
Okay, there is a question. If we fix some A, like you did the set 20 minus 20 and 1000, and we compute the first level cohomology and then second level cohomology, the second level cohomology, we will get the non-zero entry, right? And if this is true for any choice of the set of we take arbitrarily every time it is true.
That's a good question, but actually the local homology is an Artinian module, and in fact this will be 0. So for example, for I equal to 2, yeah, this will be equal to 0 if I is large enough. Yeah, so all the components of I is large enough. So it is not true that all the components of this are non-zero. It is true that this will be non-zero, but yeah, the non-zero component tends to be somehow small, negative, yeah, in some sense.
So what is a good choice for A then? So it is better to choose A smaller, like smaller than the graded vector what we are getting from the ideal I.
Yes, that's also a very good question, but I'm not sure but at least I can guess. I can give you some guess. So I think this will be non-zero if and only if. But I'm not sure. I have to check this. Yeah. So the first component should be non-negative. So A1 should be non-negative and at most 2. And the other component, I think A2, A3, A4. At least they should not be all negative. Yes. So I guess A2, A3, A4 should be 0. Yes. So for example, this would be a this could be a good choice. Yeah. And A2, A3, A4 are all non-negative. Sorry, negative, and their product is 0. So I think this is a good choice.
And
So,
what is a good reference for this theory, and what?
Yeah, I think various paper by Nguyen
Chung.
and Nguyen and Nguyen and Terai. Now Naoki Terai and Nguyen. Yeah, I'm not sure which paper, but paper by these people at maybe between 2011 and 2016 something. You should find discussion of this, but yeah, I'm not sure. This is good to think about. Yes.
In fact, this way, the theory is quite. I'm not sure whether this is a relevant question or irrelevant one, but there is a special way to find the Alexander dual with respect to a particular vector, which is given in the book of Miller and Strumfels.
Yes, yes.
So the theory is very much similar to that, but there we were, yeah, I can see there is some similarity with the Alexander dual of an ideal with respect to a given vector. But this is, yeah, but here something else is happening. This is new for me. Yeah.
Yeah. Okay. So let us try to compute this using Takayama. Yeah. So where now our A is 2, 0 minus 2, 0. So so as above, we have computed this. Yeah, we have computed this above. This is our delta A. Right? The degree complex in this case is mt y and t. And the negative support is a cos v. So if you compute the first local cohomology in degree A, then it's isomorphic as vector space to so this is 1 minus the cardinality of negative support minus 1, right? And so this is minus 1, right? Okay, and if you write down the complex of simply so chains, the reduce complex of simply so chain for this, then you get this. So ky kt this in degree 0, right? And you have something in degree minus 1 because this guy is non-empty. This complex is non-empty. And so you see here that there's no homology here, right? No reduced homology here.
So it's a kind of Poincare duality kind of thing. You are using the formula of Takayama.
Yes, this is Takayama.
It's a similar kind of a Poincare duality where you are relating the cohomology with the reduced homology. Yeah. But this is in a different setup. Yeah.
Okay, so you see that it is 0. Yeah. So H1 is really 0 as we expected. And similarly, you can compute H2. So the only difference here, you will get 2 minus this. And so everything goes through except that here you get zeros simply so, reduced simply so homology. And here you see that you have one cycle here, right? Y minus T is one cycle here. So Z is isomorphic to K. Yes. So yes, so this is really non-zero. Okay, so that's what Takayama does. And maybe for the remaining of the time, we do one more example, maybe a simple one on depth of ordinary and symbolic powers. Yeah? It is 2.4 or 2.5. So I take another idea. Take this or the other example. So these are both example of S idea of cycle. Yeah? The first one is a triangle, and the second one is a square. And in both cases, we want to compute f of r mod I to the power n and depth of r I to symbolic power n. So okay. So maybe we start with this one. So in the morning, we talk about the result of Channam 2. Yeah? And he proves that the lim depth, yeah, the limiting depth for the case of S idea, yeah, it is equal to the number of bipartite connected components. So in this case, the first example is a triangle, right? So this means the lim depth will be 0. Yeah. There is a connected graph, but it is not bipartite. So that is the lim depth, and okay, here I cheat a little bit, but actually one can also prove that as soon as this becomes 0, then it will become 0 forever after. So so if also in the case of S idea, if that this equal to 0 for some n, yeah, then it is also equal to 0 for all powers from n. Yes, so we'll we only need to care about the first position where that of this becomes 0 and the position before it, right? So first, if you compute that of R mod I, then what will you get? So you see that this you see from the primary decomposition, right? You know that I equal to I has this primary decomposition. So from this you see that the depth is at least 1, right? Because the M is not belong to the associated prime. But you also know that we have the formula that depth of M is at most the dimension of M, right? Or even at most the dimension of associated prime. Would be in associated prime. So in this case, you see that dimension of everything in the associated prime of I is 1. So this is most 1. So this tells you that the depth of I is 1. So how about the second power? So that is the first power. And it turns out that in this case, yeah, you can compute, for example, by Macaulay tool. Yeah, you can try by Macaulay tool, and you see that the second that is 0. Yeah, it is easy to compute with a computer, and to prove it, to prove something has depth 0 is also easy. Yeah? You only need to check that M is an associated prime of I squared n. So this, for example, you can check that this is true because I squared all of m. Yeah, this contain x, y, z. Yeah? X, y, z is give you a so-called element in R mod I squared. Yes, so after you know the result, this is a little bit cheating, but after you know the result, then you can prove easily that it is true, that of I square is 0, and so we conclude that of I to the n is 1 if n equal to 1 and 0 otherwise. Yeah. So how about the symbolic powers?
In the case of I square, we can't apply that graph result of Chung. Yeah. The number of bipartite components. Oh, yeah.
Yes. Sorry. This result is only give you the asymptotic value of that. It does not tell you the small value of the depth of the small powers. depth of the small power. So
Okay.
in fact, many people study this question whether depth is for S idea whether depth is a decreasing function. Yeah? But this is, I think, this is still open.
There is a class of ideal for which the depth remains the same with the increase of the power.
Yes. So
just curious about it.
Maybe the nicest class is if you take ideas generated by a complete intersection. Yeah? So ideas generated by a regular sequence. Then for this class, the depth remains constant. Yeah? So there is maybe the nicest class. Okay, now, yes, you're welcome. So now we know that we can compute the symbolic powers via this primary decomposition, right? This tells you that I is unmixed, so the symbolic power is just this intersect this, intersect this. So here computing the depth is, we are lucky because computing the depth here is easy. We see already that M, the associated prime of this guy is known. Yeah? This is from this primary decomposition, we know the associated prime. It does not contain the maximum ideas, so the depth is at least 1. But also from here, you see that the dimension of this guy is 1. So the symbolic power in this case has depth 1. So the second case is actually not that difficult, yeah, because we have a very nice result. So this is the second case. This graph is bipartite, and there's a result telling you that for bipartite graph, symbolic powers and ordinary power are the same. So for our idea, yeah. So for our idea, we only have to work with the ordinary power, and also by the result of Chen Nam Chung, we know that the lim depth of the ordinary powers will be equal to the number of bipartite connected component, which is 1, right? This is a connected bipartite graph, so the lim depth is 1. And also it is true that if the depth is 1 at some point, then it is 1 forever after. Yeah. This you can also find in the paper of Chen Nam Chung. Yeah. If depth of something is it attains this minimal value. This is actually the minimal value of all the depth. Yeah. 1, then it is equal to 1 for all m, at least n. And okay, so you can start to compute the depth of small power of I, right? So okay, and you can try this. You can first you look at the primary decomposition of I, then you get x. You can check that it is x z intersect with y t. And okay, so from here you can, because you have that depth of I mod I is at least one, because m is not in the associated prime of I. But okay, in this case, depth, the dimension of I mod I is 2, but there's a way to prove that this depth is also equal to 1. So for example, you can do this exact sequence. This has depth 2, this has depth 0, and so using the depth lemma, then you can prove that this must have depth 1. And so the conclusion here is that this guy has depth 1 for ON. Yeah.
You are using depth lemma here?
Yes.
It is better to
There are also other ways. Yes, there are also
it
other
is
ways.
better to state the depth lemma for the participant.
Yes. So the depth lemma is simple but very nice and very useful. So if you have an exact sequence of finally generated modules like this, then the depth lemma tells you that there are relation between the depth of these modules. Yeah? So for example, depth of M is at least minimum depth of P and depth of M plus 1. And then the depth of P is at least the minimum of the depth of the other two guys. And finally, depth of N is at least minimum of depth of P and depth of N minus 1. Yes, so using this and using this, yeah, this, so this has depth 2, this has depth 0, then from this you see that this has depth at least 1. And from this you see that depth of M is at most 1. So that must be 1 in this such a situation. Okay, so I think these are examples for today.
May you a little bit explain about the exactness of the sequence, particularly from the injective side? From the left side, the exact sequence above you mentioned.
So we call the map F and G. Yeah? F is the map. So F and G will be linear map of R modules, just like when you have definition of linear map of vector spaces. Here you have the notion of a linear map of R modules, just exactly the same definition. And this is an exact sequence if and only if the sequence is exact. meaning that F is injective, V is surjective, and the image of F should exactly be equal to the kernel of G.
In fact, in the above example where you have used depth lemma, if you go above, just in this example, it's a kind of Chinese remainder theorem is working where, yeah. So I was just curious about the injective part on the left
this
side.
part, right? This part,
Yeah,
right?
yeah.
So actually, this is a nice exercise on exact sequence. Yeah. So you can start with just any ring, yeah, and any two ideas. And then you get this exact sequence. R modulo I times J, and then R modulo I direct sum with R modulo J, and R modulo I plus J. Yeah. You always have a exact sequence like this, where the first map sends the equivalent class of A to equivalent class of A and minus equivalent. Okay, you can keep equivalent class of A, and the second map sends the equivalent class of B and the equivalent class of C to the equivalent class of B minus C. Yeah. So this is always true. If you apply to this situation, then get this exact sequence.
Okay. I was just thinking about whether I and J need to be co-maximal or not. In any case, I think it works for every idea. Sorry.
Yeah.
Thank you.
You're welcome.
Any questions from the IBA side? Okay, can you show the IBA people, Noman, on the screen?
Which one?
No, I have set this one to our IT
Okay.
operator. Yeah. And Junaid or Danish is there in IBA at the moment? Okay. Any question would you like to ask IBA people? Okay. It is better to hope it is it possible that you just send me the reference of the paper you was talking about? But this is seemingly very interesting result, particularly regarding to computing the depth, the limiting case, particularly the result of Professor Chung. So this is really very interesting, and I think
Sure.
you made many things clear in the tutorial, and the only thing is to practice. And regarding to students, okay, for the first time you are viewing particularly the local cohomology structure. The subject appeared to be very difficult, but try to stick with the example. Glad to see Junaid. How are you?
I'm good. How are you?
I'm fine. So, Junaid, any questions from the student side? Particularly, they were hope clarifies almost all the terms, which is regarding to, yeah, Junaid can tell you students the depth computing is not an easy business in commutative algebra, and definitely there are computer softwares which helps to compute, but this combinatorial techniques, what Hope explained, this is really very nice.
Okay, so where is the question? Yes or not? So Anam is currently doing a PhD from IB, and he's working under my supervision. So he already completed one paper in which she proved that the subalgebra basis theory could be generalized to an arbitrary graded ring. So
just out of curiosity, the work you have discussed is for depth of the ideas. So has this work been replicated in the theory for subalgebras or graded algebras? Or I can find it interesting to work in future as well?
Hope, just to tell you that Junaid is a student of Gerhard Pfister, and they are particularly experts in making the algorithms for computing depth and these kind of things in singular. So I think they pick few of the points, and hopefully they can write some good program for singular computing too. Any remark you would like to say regarding to the computing aspect of the topic? I do understand you stick with the combinatorial part only.
Okay. Yeah. Yeah. Actually, I did many computation when I wrote papers about that. Yes. So, but yeah, I don't know. I will
Probably.
think about that.
Yeah.
And I will carry. I have a question later. Yeah.
Yeah. In fact,
Not right now, but
yeah. Anyways, you stick with the combinatorial technique. This is completely different. Yeah. Any question? Any question from the audience here in Lums, Lahore?
So, any question?
Yeah, there's one question more here. Yes, who's yeah.
Sir, at the end when you proved the exactness of the sequence,
that was left as an exercise.
Okay.
So we can discuss.
There is another question. As we know that homology tells us the number of nth dimensional holes.
No, this is not. This is cohomology. I will explain.
What does cohomology tell us about?
Can you describe cohomology just layman point of view, not
as a topological view?
Topologically, yes.
no. Actually, what I was using was just simply so cohomology of simply so complexes. Yes. So and with coefficient in a field. So so what you were saying is correct. Yeah. For either. So I mean, in that case, you can take either homology or cohomology, and you get the same results. So.
Yeah. Any other question from the audience?
Question from ID?
Yeah, Junaid.
Okay, there is no question from them.
There is no question. If this is the case, let us thank Hope. Thank you very much, Hope, for bringing these wonderful stuff, particularly the result of Nauki Terai and Chung, and you explained it with a very beautiful example. Particularly, I like that result of number of bipartite.
Dr. Anam asked a question, but he didn't receive, but she didn't receive the answer. So, okay, could you repeat the question?
I just want to have an idea, has this work been replicated for the theory of subalgebras of graded algebras? Or I could say that is this a topic I can work in future? Because I find it very interesting, and since I'm working for commutative algebra, I might be interested to work
and replicate this theory for the subalgebra case.
In subalgebra case, you mean?
The theory is for, I guess, ideals.
So actually,
Junaid, thoda sa explain karna thoda sa.
I just want to elaborate the question. So actually, she is working for ideals in a case algebra of a polynomial ring. So what is the question that actually these are homogeneous ideals, I guess, in a polynomial ring over a field. So what she is asking that if we take an arbitrary graded ring, so could we generalize this theory for an arbitrary graded ring?
This is interesting question. Yes, hope if we leave the standard grading, then would there be interest?
Yeah. I mean, you can also. So for what I was talking about, I think the grading is not such a big issue. Yes, but okay. Now I remember one question about that, but I don't know if it's very suitable. But for example, it is an open question whether the depth of arbitrary depth of symbolic power of arbitrary idea can be not eventually periodic. Yeah. So what we can do and what we did is for the case of monomial idea, and in that case you can prove that the depth of symbolic power of monomial idea is eventually periodic, but there's no way to produce an example where the depth of symbolic power is not eventually periodic. There are many works on the non-Newtonian Rees algebra, and it should somehow be relevant to the question of the asymptotic periodicity of depth of symbolic powers, but we don't know how to use the existing example of non-Newtonian symbolic rings algebra to the question on that.
Yeah, thank you. In fact, yeah, in the non-standard grading setup, I think the shift will become almost the same, but there will be just a shift.
If you are looking at monomial ideas, yeah, but if you are looking at sub-algebras, then
yeah,
even the standard graded case is difficult.
Yeah.
So if you're looking at a standard sub-algebra, then, for example, if you can look at a toric sub-algebra, monomial sub-algebra, and there are not many things is known about depth of symbolic powers of toric ideas. Yeah. I think very little is.
Okay, thank you, Professor Hawk. Thank you very much.
Thank you.
Thank you.
That's interesting question. Thank you very much. And when you, I hope when you're talking about the toric ideals, so the good case is the cut ideals. The good
Yes.
case is to study through cut ideals, or maybe something else.
Yes. So I mean, you can view toric idea is a defining idea of
a toric.
Of algebra generated by monomials. Yeah, monomial algebras. The defining idea of toric usually called toric ideas.
Thank you very much. Is there any other question? Oh, I can see Abbas in the participant list. Numan, can you unmute Abbas? Abbas, you can unmute yourself if you would like to show up and ask any question. We have a participant from ISP Zanjan, Iran. Abbas, you can unmute yourself. Hello. Anyways, if yeah, I think it's time to call off the session now. Thank you very much. Now we will resume. Is there any tutorial? No, definitely. Now there is a final tea of the day, and then we can the participant can discuss these topics among themselves. Thank you, Hope.
Okay.
Thank you very much. We'll see you tomorrow. Thank you, Junaid. Thank you, everyone.
Thank you very much. See you tomorrow.